Again, thank you. The Earth is at a 23.5 degree tilt. Now, if you look at it this way, take a look at the Earth. Now, whoops, backwards. Let me make sure I'm correct with it before I give you guys that. See, I did the same thing. Now, here's an easier way to think about it. Now look at the problem. Take the Earth and put it at every spot. Take the Earth the way it is and put it at all 4 spots like this now. What it tells you is this. Take a look. The sun's rays, where are they really impacting when it's over here?
Southern.
The southern hemisphere. This is the northern, and this is the southern, the northern, the southern, the northern, the southern, the northern, the southern. So when you're closer to the sun, in the northern hemisphere, we experience winter because we don't get as many of the sun's rays, and it's not at an angle that we would like it at. If you remember back to the idea of torque, what angle was the best for torque? 90 degrees. Remember, because torque with a torque wrench, you want to push straight down when you have the wrench out. It's 90 degrees. Same thing goes with the sun's rays. If the sun's rays are perfectly perpendicular to the ground, it's the most intense. It's got the highest intensity. And if you took earth science in middle school, which some schools don't have, but some schools do, it depends. If you took earth science, you would have talked about a term called insolation. And it's spelled like this. And it's spelled, and I know it's not spelled with a U, it's not a real word. It's a combination of incoming solar radiation. Now, in earth science, what you learn is this. You learn that if the angle of the incoming solar radiation is 90 degrees, again, 90 degrees, it's the best, or it's the hottest, the most intense rays. So here, in the southern hemisphere, the part right here is actually where it gets the hottest rays at this point in time. And then when it starts to move, the rays change. But you'll notice that the southern hemisphere is getting more of the rays. And again, that's why they also have longer days. That's why they have longer days during that period. So here, for the northern hemisphere, we have summer when we're furthest from the sun. Okay? We have, because here, now to look at the sun's rays. Now they're all hitting the northern hemisphere, aren't they? That's when we have summer, when we're actually furthest from the sun. So make sure that you have this down. Again, it's a concept that's asked over and over again. And I've seen it in a lot of physics courses in college as well. It has nothing to do with the distance from the sun.
So how come like for us in the northern hemisphere, how come winter is longer than the summer?
It's not. Winter's not longer than summer.
They're all
The days are longer in the summer than the days are in the winter, but the length of the season is pretty much identical.
Really?
Yeah. But at locations like the equator, you get the same amount of sun no matter where you are. So it doesn't matter, like, what season you're in the equator. The seasons are not as extreme. As you go toward the poles, the seasons become more extreme. You get, longer winters and longer summers, or longer days, not longer winters time-wise, but longer in colder and hotter.
I want to know how come it's all kind of off topic. It's when you get, because there's like sometimes the North and South Pole, it'd be like dark all day long.
Yeah. The idea of a completely dark pole would be, for example, right here. Take a look here now. At this angle exactly. Is this southern pole ever going to get any of the sunlight? No matter which way it rotates, it's never going to get any sunlight here. That's when you have like 24 hours of darkness in the southern hemisphere. Vice versa comes around from the northern hemisphere over here pretty much. Okay? The northern pole won't get any of it.
So is there any point where it's going to be bright all day long?
Yes, so like here, the southern hemisphere is bright all day long. And here, Julian, it's switched. The northern hemisphere, which is right here, or the northern pole rather, sorry, the northern and southern pole, the southern pole at this point gets 24 hours of sunlight. The northern pole at this point gets 24 hours of sunlight. Okay? But again, that only happens one day a year because we're constantly moving. And as this moves, the angle constantly changes. Okay? But again, the whole idea is this. In the northern hemisphere where we are, the hottest days in the summer occur when we're actually furthest from the sun. And again, it looks like it's a lot further, doesn't it, from this one? But what did we say really? The orbit is really closer to a circle. There's the sun really, if you're really doing it, and the Earth then rotates around it. So it's, again, it's always about the angle. It's always about the angle really, not the distance. That makes sense? Okay? Again, please, northern hemisphere. For the southern hemisphere, though, they get summer over here when they are closest. They get winter when they are furthest. So for them, it actually does match up. So if people in the southern hemisphere were asked this question and they took a guess and they guessed that, they would be right, but their reasoning would be completely incorrect. It's not because of the distance. It's because of the tilt. If we did not have a tilt on our axis, if we were just a normal Earth, if we were just normally oriented with regards to the sun, we would not have seasons. Every day would be 12 hours of sun, 12 hours of darkness. Every single day would be the same thing. We would not have the seasons there.
So like are those days when we had those warm weather, does that mean that Earth was constantly tilting back?
No. It's not. The tilt is not it's not going out of tilt right now. It just has to do with a lot of sunlight all day long and other conditions. That's all weather. That's what you're talking about. This has to do with just location summer, location winter. It could be changing, absolutely. And then the poles are constantly switching, the north and south positive and negative poles change. But it's not like, Earth is doing this or something like that. It's talking, thousands of degrees, almost negligible, irrelevant.
So could there be an unexpected tilt change, during a certain season and it would sort of become cold in the season?
What would cause the tilt change? You tell me.
I'm saying that
You would need some catastrophic event to cause a tilt change. And that would do a lot more than just change the seasons at that point. Right? It would put us out of orbit, a lot of other stuff. But nothing is going to suddenly just change the tilt. No. An asteroid hitting it could turn us off the axis, but that would do a lot more damage besides tilting us. Okay? All right, second thing. So this was just simply looking at the seasons. Again, please take a look, people. The reason this video was actually made on Harvard students was not to, make fun of them or show that, getting a Harvard degree is not good or anything, because it's a great thing, that degree from Harvard. But the reason they're showing this video, it's used in a lot of education courses because, and this is something that I understand it, but at the same time, it's not completely understood. If you have a misconception, what does a misconception really mean?
It's like you really don't understand.
You think you understand it, but you really don't, right? So if you have a misconception or if you're taught something the wrong way, it takes a lot to get that out of people's heads. Everybody, when they were younger, thought that it had to do with, how far you are, because they're always taught it's an ellipse, right? When you're a little kid, you make the solar system models, all these ellipses, when in reality, it's more of a circle.
But Mr. Howell, it's different with being a little child because, as a child, they're trying to just show you the broad aspects of everything.
Absolutely. I completely agree with you, completely. But my thing is this. If you don't know something the correct way the first time, for example, if you think that, you know what the common mistake I see in Algebra 2, and I saw it today in my class before you came here? Take a look at this. People try to simplify this. They say, cancel the x's. But these are add-ends. You can't just cancel them. Okay? You can cancel stuff if you have like this. Like that, you can cancel the x's and you get 2/5. Because these are factors, but these are add-ends. That's an example of a misconception. So please make sure that when you go to college, guys, when you hear something, make sure you don't hear the wrong thing and write down the wrong thing. Because you start studying the wrong thing for a few days, it's very difficult to get rid of that misconception. Okay, so what they teach a lot of teachers in education courses is, if you teach something wrong, it has a really negative effect, much more than you would think. And they joke and say that you can teach something wrong once, it's going to take you 10 more times teaching it right to actually get the point across then. So it is true. Imagine if I told you guys, 2 plus 1 is 4. I'm a math teacher. Listen to me. That wouldn't make sense, would it? 2 plus 1 is not 4. But you know what? For a lot of students, they would say, my teacher told me that, right? So I'm going to believe it. So please be careful. Make sure that you're hearing the right thing. And that comes about the same thing that Ms. Gallietta tells you all the time. When you read these stuff on the internet, when you're trying to do research, make sure it's somewhat credible. Because you're reading all this stuff and you read about, I read this term. Doesn't mean the person knows what they're talking about. They can write, I can make a webpage that says, you know, that the seasons are caused by earthworms and the fact that they have a lot of protein in them. I can write a website that says that, but that's not true. Right? But do you guys understand what I'm saying? Make sure what you're listening to, what you're reading, what you're watching on a video is credible. That is backed up by other sources. Or else you might believe something, and then, you know, 2 years down the line that comes up and it's like, well, somebody told me this a long time ago, so I believe it. So make sure you understand that what you're listening to is correct. That it's not a common misconception like this. All right, second thing I want to talk about today. The question the other night on Jeopardy was, listen please, the question on Jeopardy the other night was simply, this term refers to the fact that this term refers to a location that has such a high gravitational pull that light cannot even escape it. And the answer was black hole. This was the $2,000 question on Jeopardy. It was the hardest one on the category, which I found very hard to believe, you know, seeing as it's a common thing, I think, at least black hole. So the term was this. The term was, this location's gravitational pull is so strong that even light cannot escape it. So let's talk about that for a second. Okay? It's a black hole, but let's go into what it really is now. So here's the Earth. Okay? I'm gonna give me a second. I know it's an interesting topic, but if you listen to me for a little while, it'll make sense, and I'll take more comments. First, example to start with is this.
So is that, you said that's the sun?
Earth and moon. Earth and moon. So we got the Earth. Imagine the moon is, you know, doing its rotation around the Earth. If the Earth got so big that it had such a high mass, it would eventually pull the moon to it. Again, you know what keeps us on the Earth? Because we're such a small mass and the Earth is such a large mass, we're stuck to it. If the Earth kept getting bigger and bigger and bigger, and bigger and bigger, eventually it would pull the moon in. Because its gravitational pull would get so big. Remember the example with Peter on Family Guy? When he started gaining weight, you know, Stewie started throwing the TVs in front of him and stuff, and he started getting his own orbit, or Ryan did. Now, the idea is this. An object, imagine an object like a sun. A sun is such a massive object. It's such a large object. Now, imagine a sun that collapses on itself. And these are called supernovas. Supernovas, thank you. I was thinking solar flares. That's totally different. Supernovas. So, a supernova exists when a star comes to the end of its life, pretty much. A star will either explode or collapse upon itself. Now, imagine taking, and think about this for a second logically. Imagine taking, like, a baseball. Take a baseball in your hand. Think about that right now, what it would feel like. Take a baseball and try and crush it. Can you do it?
No.
No. Imagine if you had something that could, though. And it could crush it so much that it would be the size of a grain of sand. But it has the same mass. Remember, if I take this piece of paper, it's got a mass. It's very little, maybe a few grams. If I crush it, it's got the same mass still. It's no different. It's the exact same mass. If I crush it further, it still has the same mass, doesn't it? But what am I doing? Making it more dense. Because remember, density is mass over volume. By crushing it, I'm making the volume smaller. So I'm making this a more dense object. And that's why people always joke. Have you ever heard the term, muscle weighs more than fat?
Yeah.
The reason they say that, muscle is more dense than fat. So if somebody is muscular and they look like they're the same size as somebody that might be, you know, the same size but not as muscular, their body is more dense. So it'll look like they weigh more, actually, a muscular person, than somebody that might be a little bit overweight but doesn't have as much muscle on it. So for these examples, I want you to think for now. Think about this as you crush it down further, it gets more and more dense. So take a sun and crush it down to the size of like a baseball. Okay? Like a baseball. It's going to be so dense that its gravitational pull becomes so extreme that anything in the general area gets pulled in. Anything, including light. So if you had, for example, if you were hanging out on the edge of a black hole, and there's a threshold, like any other thing that will pull you in, if you're outside the threshold of the gravitational pull, you'd just be sitting there. The minute you get within that pull, you're done. You can't escape the pull. It will suck you right in, and nobody knows what happens on the other side of a black hole or inside of it, but it's such a great pull that anything in the area automatically is taken in. That's why it's called a black hole. The minute, if you tried to send something like a camera in, if you tried to send something like a camera or a satellite near a black hole, first of all, there would be a lot of issues with communication and the electrical signal, or the, in this case, the telecommunications between the satellite and the Earth. But if you were able to get it even close to it, before it got there, it would automatically just pull it in. You wouldn't even get a vision of it, and it would just start pulling it in. And everything inside the satellite itself would collapse upon itself. It's a similar idea of why can't we see the bottom of the ocean? Anybody know that? We don't know what the bottom of the ocean looks like. Too much pressure. You send an object down to the bottom of the ocean, before it gets down there, it compresses on itself. It just implodes. The pressure is so high on it that it pushes in and it implodes on itself. So we can't see the bottom of it. What we can do, though, is send down radar or waves, like these electricity waves, and by the way they bounce back up, the speed that it takes them to bounce back up, we can see the general shape of the bottom. That's how sonar works. Sonar sends out a wave or a pulse. Based on the time it takes to get back, you know how far an object is. So for example, imagine, Bridget, I toss this to you, okay? And now Bridget tosses it back to me. Now, I did that as one example. Julian, I toss it to you now. You catch it, toss it back to me. If I were thinking of this as a wave, I'd travel the further or shorter distance to get to Bridget than to Julian. So the wave would take less time to get from me to Bridget and back. It's like taking a tennis ball. If you have a tennis ball on a big wall, if I stand here and hit the tennis ball, it takes a little time to get back, doesn't it? But if I stand right here and I hit the tennis ball, won't it be a much shorter time? So if you send a wave down to the ocean, if it comes back quicker, it means that it's higher elevated. If it takes longer, it means it's a lower surface. So if they send down an infinite amount of waves, if they take the limit as x goes to infinity, or as you send down more and more waves, you can see all the shapes of the ocean. You can see what's called a gradient or a contour. You can see what the surface looks like. That's the only way we can interpret the bottom surface. But we don't know, like there's creatures living in the bottom of the ocean that we've never expected or never seen. We have no idea what's living down there. We can't tell because they don't come up to the top of the surface. Okay, sure, maybe there's people down there. We have no idea. Okay, what adaptations have come about? One at a time. It's a good question, guys. Hold on, Terrence and Rich.
Now, how deep do you think the ocean is?
How deep? They know the depth, actually. We can look it up right now. I'll look it up right now, actually. But we don't know what's down there. We know the depth, so let's go ahead and type in.
You know what, with the sun, isn't it like 15 million degrees Fahrenheit?
The sun's temperature, you mean?
Yeah, isn't it 15 million degrees?
I don't know what the actual temperature is, to be honest. Where's the marker, guys? I don't know what the temperature is. It's something ridiculous, yeah. The sun is pretty much like, imagine having like atom bombs just going off constantly. Sorry, not atom bombs, hydrogen bombs going off. What is wrong with my mouse? What do you got? You got it already?
Says the ocean's depth.
Oh, where is that?
Right there, highlighted.
All right, average depth. It is a habitat of. Okay, unexplored is different though than actually determined. He's asking about the depth. But with the depths mean like the bottom surface has been unexplored, even though we do know the actual depth. What did you get, Edgar?
I got the maximum depth.
Okay, what does that come out to be? 10.9 kilometers? That's 6 miles. Imagine running 6 miles. But depth-wise, it is. Like around the Earth and stuff, you don't think 6 miles? A mile is 5280 feet, 5,280 feet. So we're talking like 30,000 feet. Ever hear the story 20,000 leagues below the sea and stuff? 30,000 feet is the actual max depth.
I tried to go to the bottom and 9 feet, the pressure is up, so I just jumped up.
Again, that's exactly the example, guys. Ever go to a pool that has like a 12-foot bottom? You go down to the bottom, it starts to hurt a little bit. Okay, now imagine going down 30,000 feet, not 12 feet. Think about what happened to you, obviously. Now,
So how come they can get oil pumps down and swim away from the ocean? Remember like they had, how'd they do that?
a lot of the oil rigs, they don't go down to locations that have too much pressure. Whenever they have oil rigs in the ocean, they don't go to the really deep parts that they can't get to. Because all those pipes will just collapse on themselves. Now, guys, as an engineer, they're able, and next chapter is fluid mechanics, and you're able to determine the exact pressure. So if you know the pressure, you can figure out what material you need, what size to make it to withstand the pressure. But again, when you get down, like submarines, and when you get down to the very bottom, the pressure is just 2 nits. No matter what, you don't have material on Earth that can actually withstand that pressure, okay, without collapsing on itself.
Alright, apparently the ice is melting and more water is increasing in the ocean.
Does that increase the pressure? Technically, yes. Realistically, no. It's a hard question to answer. Because the idea of water pressure is imagine you got a box of water, we're going to talk about this next chapter, but a box on the ground and water above it. The amount of pressure that's on the box is really just whatever channel of water is directly above it. So imagine if you took the box on the ground, so you got a box like this, you got a box on the ground on the bottom of the ocean floor. Okay, so we're sitting at the ocean floor. Here's the top of the ocean, okay? The pressure that's exhibited on this box is pretty much if you took the box and extended it upward. So extend it upward in 3 dimensions. The channel that you see here, see that green channel of water? That is the exact pressure that's on the box. So sure, taste here. If the water level increases, then there's more water, so this box goes higher up, so there's theoretically more pressure then. But the idea of the ice caps melting and the balancing out, it's not really raising it to the point where you're going to increase pressure at all. I mean, we're talking like tiny levels. Over a long period of time, sure, absolutely. But when it comes to like them melting now, the water level might be going up like, 0.00001 centimeter a year or something. So it's not going to do anything. But over hundreds of years, absolutely. Absolutely, when things happen. Okay? Now, let's go back to how this tied into black holes. The idea of a black hole was its gravitational pull is so strong that it just takes everything and it sucks it in. No matter what you have, it just sucks it all in. Now, the other thing that's cool about a gravitation or a black hole is this. And this is one thing that's very interesting. If you take a black hole, obviously there are several in the galaxy and universe here. If you look at its boundary, there's a theoretical, what you would call like okay, we can use the word horizon, that's fine, it is being used, but that's more of like, that's fine, we'll use horizon. Limitation, because you're thinking of like event horizon. It's a boundary, that's what I used before, but I was trying to think of another word, you said horizon. Limitation, I said also. So think of this as a limitation, okay, or a boundary, or a horizon, that's a good word. Now, the idea is the following. If you guys don't care, you can leave. We can start with that, because I've looked over like 4 times. I'm not trying to call you out, but if I have to, I'm going to do it. So relax, please. It's like the 4th time I've looked at the 3 of you. This limitation here, this boundary, this horizon, outside of it, you're not going to get pulled in. But inside of it, you automatically get pulled in. The cool part is this. Mathematically speaking, if you could actually get to the point where you're on the boundary, where you're as close as you can get without going across it, time begins to change, and things get warped. So have you heard of like the space-time continuum from like Back to the Future and stuff? Yeah. It's a real thing. It actually is. Now, what they say in the movie is no facts at all. There's really no facts in that movie. It's a great movie. I love the whole series, but nothing factual.
The Hound, Dude, Where's My Car?
I have seen Dude, Where's My Car? Yeah, they just use it because it's a fancy science word. I have seen Do It With My Car. It's a funny movie, but it's not, that's not correctly science, but they do use the term. So, the idea here is this. Time actually slows down. Time actually slows down here. So if you could, theoretically, go here for, I don't know, 100 years, and then come back to Earth instantaneously, like there's no time in between, Earth only like an hour would pass by. When here, 100 years goes by. Everything slows down. So it's very incredible to look at this. So if you're experiencing different gravitational forces and flows, time actually changes. So that's one of the effects that a black hole has on the galaxy, and that's where the worry comes about, where eventually the whole universe is going to get sucked into one of these black holes. Because what's happening is this: it's constantly pulling stuff in that comes within its horizon. So the black hole is getting stronger and stronger. So what happens if it keeps getting stronger? What if it starts pulling in things like planets then, That's the idea that people propose. We're far from that happening, obviously. But theoretically, sure, that could happen.
My question is like, alright, so if I'm on a black hole, I guess, for like 100 years, like, would I turn old and come back like an hour later? Like, everybody gonna see me like old?
So do you stay?
Time would feel like 100 years went by, right? But your body would only age an hour.
Oh, wait,
So for example, imagine sitting here
That's
imagine sitting here for 100 years, and you're just sitting here, but you only age an hour. That's what would happen. You see what I mean by that?
It's like Narnia.
Yeah, kind of like something like that, where like, ever seen, what's the original? No, is Narnia, is the exact same
It was
thing?
like she went in and she came back
Yeah,
and
there's
she was like, she been gone for like a minute. She was gone for like 3 weeks though.
The other one I've seen like that is also Jumanji. Remember Jumanji?
Yeah.
When they get sucked into the game and like all this time goes by, when he comes back, not as much actually goes by and stuff.
So that means like graphic. So when he is past that,
What? That we don't know. See, I can't answer.
but mathematically.
Mathematically, you're getting sucked in. Yeah.
So does that mean like this time still slower and as we closer to like?
Theoretically, yeah, you would think that way, absolutely, but realistically, you're gone. So, again, guys, you could never get here. You couldn't get here. It's not possible.
But I was watching this documentary about black holes, and they were like, if you get sucked in,
Guys,
it was like you'll be at 2 places at once. It was like it'll be simultaneous. Like you'll be living in the black hole, but like say if you was in a spaceship and then you send your friend out, like the person would still see you all the time you're in the black hole. How does that?
I don't know
It
too much
makes
about
sense
that.
to me.
The whole idea is what happens inside of it, we don't know. So these are all theories. So I'm sure, was this like through the galaxy or the universe
Yeah,
or
we
History
watched
Channel,
History
right?
Channel.
Yeah, a lot of these shows are really good, but they're all theories. Because again, it's a theory because we don't know actually what's going on. Or, I'm sorry, it's not really a theory, it's more of a postulate. A postulate. Remember in geometry, a postulate was something that couldn't be proven, but we thought it was right. That's one of the ways you think about it. I don't know too much about that. I know the general idea, but not much more. Okay? Now, before tomorrow, what I want to do is end today by looking at the last problem from last class. Take out the torque equilibrium problem, and I'll explain why we got zeros at our answers. That was the reason I wanted to go over this. So let's take a look back here.
Wait, on the left?
Let's take a look at the example from the other day. This is where we left off, so go to this page, please.
Mr. Howard, is that like, was that you just said,
What's the question?
now, you said how you said it may be true, but it can't be proven?
It's not true.
So is it like basketball, when they say if I was doing your shots, it may be true, but it's not true? I made this shot.
I mean, the thing with that is like there's so many other parameters that are affected. Like you can follow through all day long, right? But if you don't have enough strength, it's not going to make the move.
Yeah.
If you push it with this finger too much, it's going to start to spin it this way and then move. So that issue comes in. I think what you're thinking is the idea that the roll is better. When you follow through, you get the nice backspins. When it's the rim, it falls better. Mr. Simpson asked me that the other day, actually, to look it up. I got to do that still. He asked about which finger do you really want to instruct kids to follow through with? You know? He's like, is there a scientific, he instructs people one way, but he wants to know, is there any physical evidence to say that you should follow through with this finger, or with this finger, or with this? Like, clearly it's not your pinky, we all know that. Follow through with your pinky, it's not gonna work. It's going to be one of these three, obviously. Question is, which one is it? Your coach will tell you one thing, he wants to know, is there evidence on this? This is what's
It
best.
should be a 50 degrees of pain.
I don't know, don't play my business now.
We're gonna take the rest of the period.
Yes.
So, the problem from the other day. The problem from the other day.
You got zero.
Yeah, when you do this, you get zeros, and everybody's like, wait, why am I getting zeros, Mr. Howell? You got this.
We got 0 there one.
Okay? Now, the easy way to explain this is as follows. First, with the setup we had, one way you can think about it is, well, all of the forces are just zero. Well, if all the forces are zero, is there any torque or is there any force on it at all? No, it's not. Because again, remember how this works, people. This one here really means one F1. There's really one F1 here. So this is your matrix that you get. This is really the F1. That's F2. That's F3. So there's one F1. There's no F2s. There's no F3s. So F1 is equal to 0. That's what this is saying, really. This is the equal sign here. Remember how this came about. This is saying F2 equals 0. This is saying F3 equals 0. We really don't want zeros here. We want to know what the numbers were. Now, the only time you're going to get numerical answers here is when you actually go back to your problem and start looking at the problem in a different sense. When I am pushing up on this object and pushing up at this angle and then down on F3, what's happening here really? What's happening at this location? Can somebody explain what's going on physically at the pin?
At the pin, that at the 90-degree angle, pushing it up, still going.
So it's kind of, what is it doing to the pin then, really? It's putting like a...
Yeah, it's not pressure, but like, I don't know the word.
It's not pressure, yeah, it's not pressure. What's the word we're looking
It's
for?
like, it's going like the pin's gonna move with the beam, but I don't know, what do you call that, rotation, rotating?
Okay, so this is pushing a force up, right? So to counteract the force pushing up, the pin has to push back down, right? Equal and opposite, we know that?
Yeah.
So it's putting like forces or stresses on the pin. It's stressing the pin. It's not a pressure, because pressure, if we go to that, we're going to talk about force over unit area. And right now we're not talking about area. So we can't say pressure. What we can say though is it's stressing the pin. So the pin, as a result of these two forces pushing up, is pushing back down. The pin is also, from this one pushing down, the pin is also pushing back up. Well, this is pushing the pin to the right, so it causes the pin to push back to the left. And this is pushing the pin or pulling the pin. It's taking the beam and it's kind of pulling it this way. So the pin is going to pull back that way. So what you have here, and this is where it gets a little bit more complicated, you have what's called a reaction force. You have a reaction force. So for this problem, I didn't give you the reaction force. If I gave you the reaction force would be whatever these numbers are. Again, the pin is really reacting backward on the object. So if we're writing the FPD for this object, we see that we have, yes, F2, we have F1, we have F3, but we really need some numbers here. Okay, so doing this problem without the reaction forces, you're not going to get numerical values. So if I told you, as a result of these, the reaction that's left in the, let's see, that's right, that's left. Let's say that the net result for this kind of a problem here is as follows. We have, due to the two forces that are horizontal, F2 and F3, they're not totally horizontal, but part of them are horizontal, F2 and F3, there's a reaction force of, let's say, 20 newtons here. Now, due to the fact that F1 is pushing up, F2 is really pushing up, F3 is pulling back down, we'll say that there's a resultant of 30 newtons here. With those two values now, your sum of the forces in the y and the x have an additional number at the end of them. So for example, sum of the forces in the y direction, which is this equation we did the other day, in the y direction, we've got F3 acting down, F2 acting up, F1 acting up, but now we've got this acting down. So at the end of its equation, we got to put a minus 30 in there. For the, I'm showing you that the other day I didn't include this. It's two different scenarios. Okay? For the f of x here, as a result of F2 pointing to the right and F3 pointing to the left, there's a result of a 20 Newton pull there. So this has really a positive 20 Newton here. Why was this negative 30? Because it was acting down. Again, acting down 30. And then it was positive 20 because it was acting to the right, which is positive. Now, if you take these numbers and move them over to the other side of the equation, remember how we had a 0 here? If you move the 30 over, what is it going to become? Positive 30 and a 20. So this here, when I write my equations down, this was Fy here. This is really going to be a positive 30, and this is really going to be a negative 20. And if you try your matrix this way, with your reaction forces actually listed there, you're going to notice that, okay, you might actually get numerical responses now. So for this example that we started with the other day, the problem is that without actually looking at the reaction forces at the pin, the only scenario that will make this equilibrize or in equilibrium would be to have the forces equaling 0, which is what we got. We got all zeros as our answers because it said that, well, if the pin doesn't provide any force back, there must be no force in the beginning to start. Again, if I push on this desk, it's pushing back. There's a bunch of screws under here. Those screws are also pushing back, believe it or not. So if you pull apart something, the pin has to resist it. So without these two forces here, without these resistive forces listed, it's as if there's no force applied at all. That's why these came all to be zeros. But showing those two forces, we can then say to ourselves, all right, with those two involved, now let's try it and see what we get as a matrix. And you're not going to get the zeros there.
So we have to solve for the stresses.
So the stresses that occur on the pin are like our vertical lift up and down. And we're pretty much moving them over. You know, like this is plus K, H and K. This is like a vertical shift. So this is like your overall result on the pin. We'll move it over to get it over here so it's in standard matrix form. Standard matrix form wants numbers on this side, variables on this side. So you move the 30 over, it becomes a positive 30. Again, I added 30 to this side, I put a 30 over here. But remember, we took our three numbers over here and we listed them over here. Okay?
So we have to solve for those? Solve for the stresses, or are they going to be given?
No, okay, so either one of two things. Either you're going to be given F1, F2, and F3, and you find the stresses on the pin, which is an engineering application, because you want to find how much stress is acting on that pin, will it snap or not, based on the material properties. Or you're told what the stress that the pin can allow, which is what we're telling here. The pin can withstand 30 here and 20 here, so what will the forces be on the actual object then? So in the end, either way, you solve for one or the other. But try the same matrix real quick, and I might have it still on mine. Let's see if I do. Actually, I don't think I do, because remember it froze. Try the same matrix, guys. Go into your matrix, but change that last column.
Computer unplugged.
You got F1, F2, and F3?
Yeah.
I know, it's just
Go to the program.
because it changes the Windows settings on your computer when you run this program. So unfortunately, it does that. Thank you, though. So you got, for your matrix, let's see if I still have it in there, though. No, I don't even have mine in here. No. All right, so when you do this yourself, if you reduce this now, again, this is not my matrix. This one, Julian, you still get the ones, right? Right, Julian? Okay, what are the numbers here now?
12, 25, and 33.1, 6.8.
All right, so now that we have the forces that result on the pin, we take those forces into account also from the pin. When I do that now, we see that F1 is now 12.5. The second force that we had, that middle force, is 33.1, and F3 is only 6.8. Let's take a look back here at our original. This is F3, that's going to be 6.8. 33.1 will be this one in the middle, F2, and then F1 will be 12.5. So those three values give us our result. I wanted to make sure we went over that, because you didn't get 0 as a mistake. You got 0 because there was no reaction at the pin. For the pin to have no reaction, there must be no force on the object. If you put any force on any object, I put force on this, there's a reaction. But when there's no reaction at the pin, which we didn't include, there can't be any forces. That's why you got zeros as your answers originally. The minute we go back and include the pin, we include the pin forces, we have to include them in some of the forces in the x and some of the forces in the y. Here's a tough question for you. Why aren't the pins included when you look at the torque? Here's the torque equation right here. Remember this torque equation? Why aren't the pins included in the torque?
Because the pins really don't define about like how much about the torque because it's just keeping it in place.
Very good. The pins force is just keeping it there. There's another reason also. That's exactly right. The torque is applied on a force out here, right? What do you notice here? When you want to find torque, don't you do the force times the distance?
Yeah.
Again, force times distance. We did F1 times 5 meters. That's right here to give me the torque. Well, what's the distance between the pin here and the force here? 0. So what's the torque going to be?
0.
Remember, torque is force times distance times sine of theta, obviously. But if you look at the force on the pin, how far is the force and the pin itself from each other? It's 0. Here's the force. It's right there. The force is being applied on the pin. The distance between that force and the pin itself is 0. They occurred at the same spot. So R turns out to be 0. So Julian, your answer is right. Because this is only applying a force. How come? Because R, or the distance, we call that R in class, is really 0. And that's why you don't have to include it in the torque. So on your test, and we'll talk about this on Thursday more with an example, what I want you to remember on your test is, when you have this kind of a problem, if you're just asked to set it up, you might not have the reactions like that. That's just a setup. But if you're solving for the forces, you need to know what the reactions are and include them. And they'll be given on the diagram.
This is not a regular torque. This would be equilibrium, right?
Correct. So torque equilibrium, absolutely. Okay, and we're calling that rigid body equilibrium. That's what they call it, rigid body.
Did you solve for the 30 and the 20?
I given. Again, guys, given, the 30 and the 20 are given in both those examples. I'm going to leave you with one thought for tonight before Thursday's review. Today's Tuesday. You guys have 2 nights to study on your own before Thursday. I recommend you do it. Please don't come in Thursday asking me questions that are simple things that you should have studied. Okay? Thursday we're going to review, Friday's the test. So you have 2 nights to study before the review. Do not wait till Thursday night. Okay? What I recommend though, think about this one other thing. Think about a roller coaster. We're going to talk about this quickly on Thursday. If you look at a roller coaster, so it starts up here, right? It goes down the track, it goes loop-de-loop, it comes around here. What kind of motion does a roller coaster exhibit that we've been looking at? What is it? Circular. Circular. Very good, Star. Because here, take a look. You have a radius. See how this is a radius, and then you loop into the circle, and then really this is actually part of another circle? If you were to continue this portion here is really part of another really big circle coming back around. This is like your radius of the inner circle here. This part of the curve right here is part of another really circle. So every time you have a curve of any sense, go back, come on. Anytime you have a curve here, what you're really looking at is that it's really part of another circle. So anything that goes on curves is constantly really in circular motion, just for little parts though. Until it hits the loop-de-loop, then it's in circular motion the whole time. But you're going to notice that these are not really circles, actually. These are not really circles, and we'll talk about them more on Thursday. But what I want you to remember is this. If you need to figure out what the velocity is in here, you can use your circular motion formulas for this also. Okay, just consider that for the next 2 days. I just want to leave you with that thought. Do you want practice problems to work on the next 2 days?
Yeah.
I think you should. I'll give you some out of the textbook that might be good, worthwhile ones.
Yeah, man, no practice problem.
Okay, it's up to you to do them. I'm not going to check you guys. It's for your test. It's up to you to practice. So for those that would like some extra practice, which is most of you, I think.
Do you know what? Nah, I miss Aces and Aces.
She got money though, but she don't like people talking. She don't like people doing work like that. Nothing that's not class.
She really be preaching to us. I ain't talking about the trouble here. She was first time to talk about gonorrhea. Think about it. Let's talk. You go like this?
Are you hard-headed?
I wrote all the next.
That one, one of our table.
I wrote the thinkers, the vaccines. Three vaccines, 2 dailies. Then we got, hey, we talk about the vaccines. I wrote all the discarding cards right now.
Okay, try those ones if you'd like to for the next 2 days.
Oh, Johansson. Oh, I'm looking at this stuff in my head. What position?
I can even write it down.
You know what they need? What? My card instruction. No, card instruction. No, sends.
Second. How's your tour go, Star? Can you give a tour?
Oh,
How'd it go?
are we going to that copy?
Comes off like computer.
No, I don't know. What's
You don't need it, you don't need it. Like, always bring it.
Is he recording? I have known all over the world because I got one ambiguous high there.
You should put your name there, though.
Can you tap the stop button right there?